right, for those of you who are playing at home alone, pause the video and do the questions and then start it back. So for those of you who are here with me, we're going to get started with the answers to this. So number one, this should have been your net ionic equation. Remember that potassium and nitrates are always soluble. So these are the only things that we're going to be reacting. This is going to be reacting to form a precipitate. And they talked about that forming a precipitate here. So that should have been your clue. Remember, lead is a pretty big ion. Lead-2 is, it's going to have a lot of mass or a lot of electrons to it, that sort of thing. So typically lead is going to be like one that's going to end up precipitating out more often than other things. So that's always kind of a red flag to you, that if you're looking at these different things, that's probably going to be the thing that's going to be reacting. All right, so what's the best representation for, and it's also good for you to start looking at these point values. Like, what are they looking for? So net ionic equation is going to show the formation of the lead and iodine coming together. These guys are just going to be spectator ions. They're still going to be floating around in the solution, so you wouldn't put that down or put those in a net ionic equation. Explain the purpose of drying this and weighing it 3 times. Filter paper and precipitate has to be dried several times to make sure that all the water has been driven off. If that water's still in there, it's going to change your values because it's going to assume that that mass of that water is mass of this lead iodide, and it's not. In the filtrate solution, K was greater. Which one was greater? The potassium is going to be less because the NO3 was added in excess. So typically one of these things is going to be excess. The excess thing is going to be left behind. It won't have been used up. Over here. So did you get this for your value for your moles? If you wrote it out of scientific notation, it would be 0.0000512. My guess is your calculator would probably kick it back to you like this, but they didn't say in scientific notation, so you can write it down either way as long as you have the right number of placeholders.
I did not get that.
Okay, do you understand what you did wrong?
No.
Okay, so you started out with the mass of the dried filter paper, and you knew that what the mass of the material was to begin with, right? So this is the 1.68, the one, so that's the mass after the drying, okay? And this was the mass before of just the filter paper, okay?
Mm-hmm.
So this is the mass of the filter paper and the precipitate. You subtract this guy from this guy to get the mass of the filtrate, okay? That filtrate you should have identified as lead iodide. Lead-2 iodide.
Mm-hmm.
Okay, that many grams, then you're going to divide it out and by the molar mass for this guy, and that's going to give you your moles. Right? All right, then they want you to, this is the doozy. This is a 2-pointer down here, but you're still going to get points for these things. Okay? And if you got this one wrong, for example, but you set all of this up right, they're going to give you the right but wrong points. So keep that in mind as well. All right, so you're going to take this amount and you're going to do stoichiometry essentially. Okay, so you know that you've got a 1-to-2 ratio here, and that comes from your balanced equation. Okay, and then that can back you up, and that gets you the grams of iodine. Okay. So that will give you they wanted to know the number of moles of iodine. So that would be the number of moles of iodine would be here. Okay. Then you can then they wanted the mass percent of iodine. So that's going to give you, you're going to take the 0.13, which you calculated from these moles. You just multiplied it by the molar mass. And you're going to divide it by the whole tablet that you started with originally back here. And then that'll give you your percent yield for that guy. All right, in another trial, they dissolved a 55 ml water instead of 50 mils of water. Predict whether the determined percent of iodide will be greater than, less than, or equal than. it's going to be the same because we're not talking about the molarity here. We're talking about the percent of iodine in the water, and that's not going to change, okay? The water is going to be removed by that filtration and drying, so the amount of water is irrelevant in this. All right. So titrations, remember we've got the equivalence point. That's where the moles of your base are going to equal the moles of your acid. And here we've got a graph. Titration, this is a weak base. Weak base is being titrated with hydrochloric acid, which you should know by now is a
Strong acid.
Strong acid. Okay, so predict which point would represent the pH of the solution at the equivalence point. Good, Austin. Good, good, excellent. So D is the correct answer. Now, if we needed to figure out the pKa of this, okay, remember that the pH at the half equivalence point is going to give you the pKa of that weak base. So that's another good point on the graph to be very familiar with. All right, big idea 2 dealt with different types of bonding. This is still arranged in big ideas, but most of the material is still the same. And by now you guys know everything, so I can go back to kind of the big idea kind of concepts. So ionic compounds, remember, are your metal and non-metal bonded together. They tend to have very high boiling points. They're solids at room temperature. We collectively refer to these oftentimes as salts. As a solid, it does not conduct electricity, but as a liquid, since they're soluble, they break up into charged ions, and as a liquid, then they're going to conduct electricity. Okay, and if they're broken up into solids. Simple covalent, you've got different ones of these. These are your non-metals bonded together. They tend to have very low melting and boiling points because they just have to overcome these IMFs. They don't have to overcome this ionic bonding. Usually liquid or gas, but some are solids. We do have some in the solid state. Does conduct electricity? No, it does not. It does not conduct it in the liquid form either. And it depends on its solubility. Some of them that are polarized do, other ones are not, that are nonpolar. So you got to look at the polarity of the molecule. Network solids then are your diamonds, graphite, silicon dioxide, like sand. High melting points, solid at room temperature, does not conduct electricity except graphite. It's just kind of weird. Liquid conducts electricity. We don't usually see these. There's so much stinking energy that has to go into this to get to a liquid form that it's kind of irrelevant. And it's not soluble in water. And the metallic high melting points state at, typically they are your solids at room temperature as well. They do conduct electricity because they've got that mobile sea of electrons that can move the electrical charge, and they do conduct as a solid and a liquid, and they are not soluble in water. Okay, so which of the following substances will be least soluble in water at room temperature? Least soluble. Sticking with that answer, Emma? No, changing it up. All right, I think Austin has his answer in, and D is indeed the correct answer. Good job, Austin. Okay, these have, first of all, this is ionic, so it's gonna break up into ions. You should recognize that the potassium and nitrogen are going to be soluble every time, so you're going to get solubility there. This one, these are both polar molecules because they have this OH extension here. So they're going to be polar. And remember, polar molecules mix with polar molecules. Do not put on that exam like dissolves like. They will mark it wrong. They will not think about it for 2 seconds. They will see like dissolves like, and they will not give you your point. Okay? Polar molecules are soluble in other polar molecules because of those intermolecular forces. You have attractions between a polar molecule's positive or negative dipole and the other one's positive or negative dipole. Okay, so you got to talk about that in terms of polarity. You've got to talk about it in terms of hydrogen bonding. You can't just say like dissolves like and walk on. They will mark it wrong. This is completely nonpolar. And remember, if this is nonpolar, it's not going to interact with water. The water is just going to stay kind of stuck together in its hydrogen bond. It's not going to separate and allow this guy in because he doesn't have any charge associated with him. All right. Oxyacid strength is going to increase as you go down here because you're getting, this is becoming more and more and more charged, more polar as we keep adding these oxygens on. Over here, acid binary strength, the greater the size of the negative ion, the weaker its attraction for the proton, and so the stronger the acid, the weaker the conjugate base. So which one of these would be the weakest acid? Ready? All right, there you go. So this guy has more mass here, but the problem is that it has less oxygen, so it's got a less electron density over here. Okay, and remember, the greater the size of that negative ion, the weaker its attraction, and so the stronger the acid and the weaker the conjugate base. All right, behaviors of solids, liquids, and gases. Solids are packed close together. Liquids are arranged randomly and they have the ability to flow, and gases are arranged even further apart and they have the ability to flow. Collectively, liquids and gases, since they have the ability to flow, are called fluids. So let's, we also look at the kinetic molecular theory here. I don't think there was a question on that one. Yeah. If the temperature is not changed, no matter what else is listed in the problem, the average kinetic energy of the gas does not change. And I got you guys on one of these in that 2013 worksheet. So keep that in mind. All gases begin to act non-ideally at low temperatures because remember, they're going to slow down and they're able to hook up together, or high pressures because they're getting squeezed closer together. Under the same conditions, the stronger the IMF between the gas particles, the less ideal the gas will behave. N, remember, is moles. So high number of moles versus a low number of moles. Which one of these situations is going to be most ideal? Austin, you going to chime in here? Okay, no. So low pressure though, high temp. Because remember, low temperature, they're going to slow down and start to get together. Okay? All right. Gases, factors here. Don't worry about individual gas law names, but do worry about the effect of changing moles, pressure, temperature, and on the sample of gas. Okay? So C, which use the kinetic molecular theory to predict what would happen to a closed sample of gas whose temperature increased while the volume decreased. Is that your answer? Okay. So yes, the pressure would increase. So the average kinetic energy would decrease. It would actually increase because we've increased the temperature. The pressure would decrease. Well, we're increasing the temperature, so that's and the volume decrease. So because of that, your pressure is going up. The number of moles would decrease. Well, it's a closed system, so that can't happen. Its pressure would hold constant. While we're decreasing the volume, the pressure is going to increase. Okay. Ideal gas law then, you've got PV equals nRT as your gas law. See which one of these would be set up correctly. And enjoy the dog pick. We're solving for molar mass here. Got it? Austin? Austin? All right, let's talk about this guy. So the correct answer is E. Okay. Remember your, I don't know if this will let me write on here or not. I think it'll be nice to let me write. Oh, yeah, it does. So PV equals mass RT over MM. Okay, we're solving for MM. So if I rearrange this, it's going to be MM equals MR. This should be T, sorry. MRT over PV. Okay, so we want to look for somewhere that the mass is on top. So that's going to get rid of this one. It's going to get rid of this one. And it's going to get rid of this one. Okay, so now I'm between these two. What's the difference between these two? What happens to be the temperature. And remember that the temperature has to be in Kelvin. They gave it to us here in Celsius. Those little sneaky guys. Okay, so because of that, you've got to convert that into Kelvin, which you should be able to easily identify that. Okay, chromatography then. You can check on the progress of materials here. Things that are nonpolar are going to move across this polar cellulose and be able to move up further than the things that are nonpolar or that are polar, because they're going to get attracted to this and stick here. So these guys are going to move up. You got your polar solvent here, and this is your nonpolar solvent. All right. When drawing solute molecules, then pay attention to the size. Na is going to be smaller than Cl minus. Draw charges on the ions, but don't draw them on the water, but not on water. Draw at least 3 water molecules around each thing, and then show that the negative dipoles are going to be pointing towards that cation here, and then the positive dipoles are going to point towards the anion. So this is another drawing one. See if you can draw this. These are actual like released exams. These are legit questions off of released exams. All right, good. So this is what you should have had drawn. Make sure that your oxygen's bigger than your hydrogens and that your oxygens are pointing towards that positive cation. Right. Molarity and particle views. This is one of the ones that we ended on the other day when we were together in class. So remember, make sure that you're looking at the volume of the materials in there. Make sure that you're looking at the particles, how those particles are bound to one another. So rank the 6 solutions in order of increasing molarity. Pay attention to the volume, and some have equal concentration. So they may be, you know, like 2 side by side, and you just have them flipped around, but they have the same concentration. So see what you can do for this. Oh, and then I need to get orders for face masks for you guys. I'm going to make you a face mask that has one of these 4 things on it for your AP exam. Any preference up there, David?
I'm going 2.
Number 3?
2.
2? Okay. And if you want to bring a t-shirt in, I can make a t-shirt with one of those for you as well. It just needs to be a 100% cotton t-shirt, not one of the like nylon-y things. You like one of those? You don't want a face mask? To wear to the exam to look cool. Fine. That's what Eric's getting to, is number 1. Keegan, can I make you a face mask as well? Which one do you want? All right, done. Okay, so did you get these ranked? You ready to go? Austin, you got them ranked? Oh, he's got it. Okay, let's see here. So C, D, and E are all tied. Okay, so C is here. We've got 4 over 50. So if you want to do like 4 moles over, it would be 4 over point, you know, if you wanted to count these as moles, but it's 4 over 50. So you can kind of think of what that is. Let me see, that was C. D is here, so that's 4 over 50. And E is here, that's 2 over 25, but you're going to come up with the same number. Okay. Then A and F are tied, so you got 1, 2, 3, 4, 5, 6, 7, 8 over 50. And this one is 4 over 25, but it's the same number when you divide. And then lastly would be B, where you have all of these over 50. So how'd you do? Good? That one? Okay, good. I like those. All right, distillation to separate solutions. You can heat different solutions up if they have different boiling points. Remember, the thing that has the lowest boiling point is going to evaporate off first at the lowest temperature. You can then collect over one of these distillation apparatuses. You can collect that vapor and condense it back down into a liquid and collect that over here. Okay. The thing with the lowest IMFs is going to have a lower boiling point. It's going to condense away easily and leave the rest behind. Ethanol, hydrogen bonds, as water does, and it's polar but not part of the ethanol, has only LDFs because it's nonpolar, resulting in a lower boiling point. Okay, so that's our distillation process. And we end up with just that in our liquid. And which of these would have the highest boiling point? Should be able to answer this very quickly. Looking at a periodic table, boom, done. All noble gases. Got it? Done? No? David is? Good. Okay, everybody got C. Excellent. Okay, highest, it doesn't, remember, it's not the mass though. Okay, don't put down because it has a higher mass. It's because it has a more what? The mass indicates this, but it's not because of the mass.
It is more polarizable because it has more electrons.
That's what they want. Okay, those are the buzzwords they're looking for. Okay, it has more electrons and is thus more polarizable, leading to higher IMFs, causing a higher boiling point. So you've got to put all of that stuff down. Okay. See, they even put that in here. All right. Yep. Okay. Deviations from ideal behavior. At which value of temperature and pressure will the gas N2 behave least ideally? Austin, do you have an answer in for this one? Okay. So A is going to be the answer. Remember, it's low temperatures, so we're going to eliminate these automatically, gone. And then the next thing we want to look at is pressure. So low temperature, high pressure, it's going to be A here. Hydrogen bonding then is seen in a lot of different molecules. It's kind of like a sandwich between. We've got the hydrogen connected to either a fluorine, oxygen, and nitrogen, and it gets attracted to a fluorine, oxygen, or nitrogen of another molecule. Okay. Remember, you want to be on the phone. We've talked about that many, many, many times. Okay. This is actually a problem on my, I think you guys saw this one on the 2013 exam. My pre-AP kids are going to see this tomorrow on their test coming up. Don't tell them. Shh. Got it? No, not yet. Thinking about it. Austin's playing around. Is that your final answer, Austin? All right, two of the arrows point to hydrogen bonds. This is a hydrogen bond. This is a hydrogen bond. This is a hydrogen bond. Remember, a hydrogen bond is intermolecular. It's between molecules. So we have three that are pointing to hydrogen bonds. So that one's out. 3 point to intermolecular bonds. Yep, I'll buy that. 3 of the arrows point to, did I do that right? Yeah. 3 of the arrows point to interactions that are significantly stronger. No, these are significantly weaker. And 2 of the arrows point to non-polar covalent bonds. These are covalent bonds. They are polar covalent. They are not non-polar covalent. So the correct answer is B. All right. Coulomb's law then. Coulomb's law, we've got ionic compounds can dissolve in polar liquids like water. The ions are attracted to either the positive or the negative part of the molecule. There's kind of this tug of war going on. The solid is pulling individual ions back out of the water where it exists in equilibrium based on how strongly that's attracted. We can predict the degree of solubility for different compounds using Coulomb's law. The smaller ions, the closer together they are, and the harder it is for the water molecules to pull the ions away from each other. The greater the charge on the ions, the harder it is for the water to pull them away as well. So predict which of these pairs would be more soluble in water based on these Coulombic attractions. There's not an A, B, or C, or D here, guys. It's just which one of these is going to be stronger, which one of these, which one of these. All right, let's look at it real quick because the bell's about ready to ring. So NaF is going to be, because we have more effective nuclear charge here. Here, same difference, more effective nuclear charge. And lastly, this guy is because we are fluorine, okay? And we will pick up an entropy and solutions mañana, okay? Get out and enjoy the weather today. It's supposed to be fabulous. I haven't been out there yet, but I wanted to go ride my bike, but they're talking about it being kind of windy, so I don't know if that's going to happen or not. All right, I will see you guys tomorrow.
See you, Lippy.
Bye, hon. Stop recording.